This video will begin to talk about the foundations of linear algebra, especially around matrices. And we can't hit everything, so we're going to focus on these 5 topics to begin with. So what is a matrix? A matrix is a rectangular array that's formed by m rows and n columns, and we would say that's an m by n size matrix. We can add and subtract matrices when they are the same size. Scalar multiplication can be done where we're going to take a scalar on the outside and multiply it to every term inside the matrix. And when we multiply matrices, we have to pay attention and make sure that the column size of the first matrix is the same size as the row size of the second matrix. And then we can actually multiply those two matrices. So let's go through a few examples. Say I want to add two matrices. When I add my matrices, I want to add elements that are in the same location within each matrix. So in this case, I would say 4 plus 3, 5 plus negative 6, or 5 minus 6, negative 1 plus 7, so on and so forth. And then I can simplify each element to the point where I have that these two matrices added together become 7, negative 1, 6, 4, 0, and 9. Now when I want to do scalar multiplication, that's where I have a scalar on the outside. I multiply it to every term inside. So this becomes 3 times 4, 3 times 5, so forth. And then I just simplify so that I have just this, my matrix there. All that scalar being multiplied through everything. Now when I actually multiply, again, I want to make sure that my column size of the first is the same size as the row size of the second. So here I have a 3 by 2, and here I have a 2 by 3, which means I can multiply them since I have that same column and row size. So what I do is I take my first row of my first matrix and multiply it by each column in my second matrix, and I add those terms together. So I can see 2 times 1 plus 3 times 6. That's going to give me my first element. Then I'm going to do 2 times negative 1 plus 3 times 0. That'll give me my second element in my row. And then the 2 times 2 times 4 plus 3 times 2, and that'll give me my third element. Then I'm going to go and do the same thing with my second row to each of those columns to give me my new elements. And again, I'd follow the same pattern and take my third row, multiply it to each of the columns to give me my 3 new elements in that third row. And if I simplify everything, here would be my solution. Now, I can, in this case, if I flipped these around, I would have a 2 by 3 and a 3 by 2. So I could multiply them together, but I end up with a solution being a 2 by 2 matrix. So one of the key things to remember is that multiplication of matrices is not commutative. That's important to remember. Now if you hear the term the transpose of a matrix, and it's going to be written as A with the superscript T. And what that means is we're going to flip the rows and columns of a matrix so that the first row will now become the first column, the second row, the second column, and so on and so forth. So if I have this 2 by 3 matrix A, the transpose would become a 3 by 2 matrix, where this first row becomes my first column, and so forth. So I'm going to take that first row and I'm going to plug it in for my first column in order, 3, 4, and 1. Then I'm going to take that second row and I'm going to plug it in for my second column in order, 2, 5, and 6. And that's my transpose, which you will work with from time to time with matrices in linear algebra. So it's good to know what a transpose is and how to use it. Now the next term is the determinant. Now we often use determinant in certain situations, and we don't often talk about, well, what is the determinant? The determinant is the sum of the entries of a row or column of a square matrix A multiplied by the respective cofactors. There's a lot of words in there that are important to pull out. First, to do a determinant, it has to be a square matrix. So you have to have the same number of rows and columns. The second thing is this idea of taking the sum of a row or column. So we're going to take those entries, add them together, but first we have to multiply them by a cofactor. So we have to find the cofactor. And that means we also have to find the minor. And the minor is a smaller version of a determinant. So we're going to get to that here in just a second. So say I want to look at this matrix. If I take and just look at the first entry, that would be the first row, first column. So we're going to find the minor at 1, 1. So I would circle my first entry, and I'm going to cross out the row and column that it's connected to, and then I would find the determinant of this 2 by 2, which is what's left. So if you remember, to find the determinant of a 2 by 2, I take and multiply the diagonal. So I take the first diagonal, subtract the second diagonal. And that would tell me that the minor here is -3. So the minor of 1, 1 is -3. The cofactor is then taking that minor value and then multiplying it by -1 raised to the I plus j, the location. So the cofactor here, -1 raised to the second power is +1. +1 times -3 is still -3. And if we think about the sign pattern where it goes plus, minus, plus as you go row through the rows, and same thing as you go down the columns, it makes sense. I'm saying that this is going to be exactly what comes out as the minor, whereas if I use the second term, it's going to be the opposite of whatever comes out from my minor. Now, why is this helpful? When we get to larger matrices, we have to find those cofactors to be able to find the entire determinant for that matrix. 2 by 2s are easy. You just find the determinant by multiplying the diagonals and subtracting the second diagonal from the first diagonal. Not hard at all. And it's probably what a lot of you have done even in your Algebra 2 classes. When we get to a 3 by 3 matrix, now we have to pay attention. So we take that term. Here we're going to say like the first row, we take the term, and we're going to multiply a by its cofactor. So we got to find the minor of these parts and then multiply it by -1 raised to the locations power, sum of the locations. Then I'll do the same thing for element B plus element C, because that's that entire row. It's the element times its cofactor. Another way that this can be done, which can be simpler than this process, especially as you get to large matrices, is to try to turn the matrix into a triangular matrix. And a triangular matrix is one where you have your diagonals and everything below is zeros. If I can do that, then the values that are on the diagonal can be multiplied together to give me that determinant. That's a much easier way when you're thinking much larger size matrices. But it only works if I can create the triangular matrix. So let's look at the cofactor method for this matrix A. I want to find its determinant. That's why I got those vertical bars. So I'd first need to find, in this case, instead of doing the first row, I'm going to do the first column just to show you that it can be done. It doesn't matter which I use. So I'm going to start with element 1, 1. And so I'm going to find the cofactor in this location. So that's -1 raised to the 1 plus 1. And then I'm just finding the determinant of this 2 by 2 that's left. I simplify and I get to 222. Now I'm going to find the cofactor of my element here at -6, which is row 2, column 1. So that's the cofactor of 2, 1. So when I think about -1, that's the second row plus the first column, so that's 2 plus 1. I got to pay attention to that. And then I'm finding the determinant of this 2 by 2, 3, 6, 5, -14. Not hard. Just got to remember that -1 raised to the third power means that that's -1. Remember, plus, minus, plus. Simplify and I get down to 72. Now I'm going to do the third row, first column. And I'm going to, again, find my cofactor. When I simplify that determinant multiplied by -1 raised to the fourth, I get positive 33. Now to find my determinant, I take the element, multiply it by its cofactor. So in this case, I'm going to do the elements from the first column, multiply it by its cofactor. And I use that first column because this one term becomes 0. So I didn't even have to find its cofactor because I knew by having the 0 there, it disappears. I simplify that, and I get down to that the determinant of this matrix is 12. Well, what if I went the other way of using a triangular matrix? Well, to do the triangular matrix, I have to remember to use my my elementary operations that I'm allowed to use when working with matrices, which is I can add two rows together, and I can add the scalar of a row to that of another row. I can swap the rows if I need to. And so let's see what we have here. So if I add 3 times the first row to my second row, so that would be like 3 times 2, 3 times 3, and 3 times 5, and I'm going to add that to the second row. I end up with the second row becoming 0, -3, and 6. Now I've got a 0 here, so I've zeroed out this first column the way I need to. Now I need to see, can I get a 0 here so that all I have is my diagonal and I have my triangle. So, well, what would I need to multiply to make this become a 0? If I multiply this row by 2, -3 times 2 gives me -6, so they would cancel out. So I'm going to multiply the second row by 2 and add it to my third row. Now look, I have a triangular matrix. It worked. I can make it here. So if I multiply the elements on the diagonal, -2 times -3 times 2, I get 12. Again, found the determinant 2 different ways. Now last thing we'll talk about are inverse of a matrix. And the inverse of a matrix is that which, if I multiply it to the original matrix, will create the identity matrix, which is where it's ones on the diagonal and zeros everywhere else. And it doesn't matter if I do the original times the inverse or the inverse times the original, it'll always create the identity. The way that I can create this and find an inverse is I can create what's called an augmented matrix, and it has to be a square matrix where I'm going to put the matrix on the left side and the identity on the right side. And what I'm going to do is I'm going to use those elementary row operations and slowly turn the left side into the identity, and the right side will then be my inverse. So again, I can interchange rows, I can multiply a row by a non-zero constant, and I can add a multiple of one row to another. Those are the 3 operations I can do. Now, if I remember here, a 2 by 2 matrix, very easy. All I have to do is find the determinant, which 2 by 2 is very simple. So it's 1 over that determinant. I swap my elements at A and D, and I put the negatives on the other diagonal, and that will give me my inverse. Much easier than having to go through the entire process of trying to convert. And if I can't reduce it to that identity, then it won't work. So let's try a matrix here. So here's my matrix. I'm going to put the matrix on the left side and the identity matrix on the right side. And I'm going to try to turn this one into the identity matrix. So first thing I'm going to do, I'm going to add the negative of the second row to the third row. What that does, it gives me a 0 down here. Now I'll look and say, well, what else could I do? I could take the negative of the first or the third row and add it to the first row, because that'll cancel these out and they'll become zeros. Okay, so I keep moving here. Now I'm going to say, well, what else could I cancel? If I added -3 times the first row to the second row, I'll get rid of this term. And then I keep going. If I take and multiply by -4 times the third row to the second row, and now all I have left is to cancel out this bottom one. So I'm going to take the negative of the second row to the third row. And I have all ones on my diagonal, so I have the identity matrix, and here on the right side then is my inverse. So my inverse then is just that right side matrix. And if I want to double check, I could multiply the two together and I would see they give me an identity matrix.